Hi everybody. This is a quick lecture on Chapter 17 in your Bushong book, Digital Radiographic Technique. This is for RT 132. Okay, there's two principal characteristics you need to know. Spatial resolution, which is the ability to resolve and render a small, high contrast object. And number two, contrast resolution, which is the ability to distinguish many shades of gray from black to white. Spatial resolution, that ability of an imaging system to resolve and render on the image a small, high contrast object. Also how to differentiate between two side-by-side objects. That is resolution. Okay, and we want to bring up the concept here that the larger the object is, the easier it is to be reproduced on an image, very close to exact size, and the smaller an object is, the more difficult it becomes to reproduce that object exactly. Okay, as you remember from our last lecture, resolution is measured in line pairs. Okay, spatial resolution in the digital imaging world is referred to as spatial frequency. Okay, and spatial frequency is measured by line pairs per millimeter. And the same slide that we saw last time in our lecture is here again. So you have one line here, 10 millimeters wide. The space next to it, which is the exact same width, is 10 millimeters wide. So a line pair equals from the beginning of this line to the beginning of the next line. This area here is one line pair. And what you end up doing is taking the width of that line and doubling it. And that is read as one line pair per 20 millimeters. Okay? All right, so what you need to take away from this slide, as you go down here, you have one line pair, which equals 0.1 millimeters. I cannot even differentiate that there's a line and a space here. So if you can, that is great. But I want you to look at this red part of this slide and spatial frequency, how it's measured. Okay, so this is considered low spatial frequency, and as the number increases, this is high spatial frequency. So in the lower spectrum of the spatial frequency measurement, the larger the objects are for us to see them. So larger for lower resolution, the object has to be large for us to see. Low spatial frequency, low resolution. High spatial frequency, high resolution can differentiate between very small objects. Okay, so small objects can be differentiated at high spatial frequencies, okay, or high spatial resolution. Okay, here is a problem for you. So there's several math problems that you guys are going to need to figure out how to do, and it's not very hard. It's just trying to get the concept down. So this problem is a digital radiographic imaging system, has a spatial resolution of 3.5 line pairs per millimeter. So that's been figured out by a physicist. How small of an object can it resolve? So to find out that number, you're going to take what's given to you here, the 3.5 line pairs per millimeter. You're going to double that. So that's going to tell you how many or how much spacing for one line pair. So 7 objects in 1 millimeter. The reciprocal is the answer to these problems. So you're just going to invert your fraction so that it reads 1 over 7. And that is going to be equal to 0.143 millimeters. And so if you convert that into microns, the answer to how small of an object can be resolved on this digital imaging system that has a spatial resolution measurement of 3.5 line pairs per millimeter, it can see images as small as 143 microns. Okay, here's another problem. So a screen film mammography imaging system operating in magnification mode can image high contrast microcalcifications as small as 50 microns. What is the spatial frequency? So if you take, and we're going to convert this 50 microns into millimeters. So we're going to start off with one line pair is over 100 microns. We're going to convert that micron to millimeters. So 100 over 1,000, and this converts to 0.1 millimeters. Okay, we're just getting rid of the microns and turning it into millimeters. So then we have one line pair over 0.1 millimeters. Okay, so both of these things equal the same thing, just different units. Convert this 0.1 into 1. Okay, so that we have an easier number and we have a whole number on the bottom. So we're just converting that 0.1 to 1. So we're multiplying both sides by 10 to convert that. So the answer is going to be 10 line pairs per millimeter. Okay, that is the spatial frequency that can see 50 micron image. Okay, all right, moving on. Okay, the concept of spatial frequency. So this is Dr. Bushong's take on how to describe what spatial frequency is. The Undertaker's plain black suit, which is right here, has a spatial frequency of 0. So there's no changes in his suit from horizontal to vertical. Okay, the banker with this pinstripe suit has 0 spatial frequency in the vertical direction. So 0 change in the vertical direction. If these were all lined up, you would see 0 change vertically. But when you go horizontally, it has a high spatial frequency. So there's changes. There's line pairs. Just imagine these are line pairs close together. So this has a high spatial frequency in the horizontal direction where all the lines are intersecting. Okay? The salesman's coat has a high spatial frequency, so changes in this direction and changes in this direction, has a high spatial frequency in all directions. And I don't know if this is helpful or not, but I put it in here just in case. There's a couple of you that could be very visual. This might kick it in. Okay, this next slide, we've seen this before, but it shows the differences in spatial resolution of some imaging systems. The Gamma camera in Nuke Med has a very low spatial resolution of 0.1 line pairs per millimeter. So it does not see very good detail on small objects. It needs large objects. And if you've ever seen any Nuke Med images, you understand that. They're all blurry, they're all over the place, okay? Compared to down at this bottom, which is mammography, which can discern very small objects up to 12 line pairs per millimeter. Okay, here's another problem. So the image from a nuclear medicine gamma camera can resolve a 1/4 of an inch object, 1/4 of an inch. What spatial frequency does this represent? So first of all, 1 inch is equal to 25.4 millimeters per inch. Okay, knowing that, you're going to take the information they gave you, this 1/4 inch, you'll multiply it times the 24.4 millimeters per inch, okay? Get rid of our inches, and this gives us a 6.35 millimeter answer, okay? Then we're going to take that and double it, because remember, one line plus the space next to it. So from the beginning of one line to the beginning of the second line is a line pair. So you have to double this. And that gives you 12.70 line pairs over millimeter. And remember, the answer is the reciprocal. So we switch that, and it comes out to 0.08 line pairs per millimeter. Now, in some of the modalities, CT, MR, apparently Nuke Med, they use the unit of centimeters for the resolution. We don't need to worry about that. We're just going to stay in millimeters, okay? Okay, moving on. Spatial resolution in mammography, in radiography is determined by the geometry of the system. Or another way of saying that is it's determined by the focal spot size, okay? Mammography is the best due to its ability to have a very small focal spot size, 0.1 millimeter. Okay, spatial resolution in digital imaging is determined and limited by the pixel size. Okay, so see the difference there? Spatial resolution in radiography is determined by the geometry or the focal spot size of the beam, the geometry of the beam. Spatial resolution in digital imaging is limited by the pixel size. So no digital imaging system can image an object smaller than its 1 pixel. Okay, this next slide. Spatial resolution in digital imaging is limited by pixel size. Okay, here's a problem. What is the spatial resolution of a 512 by 512 CT image that has a field of view of 30 centimeters? Okay, so in digital imaging, as I'm sure you are aware, the matrix can be manipulated. And the smaller the pixel size, the better resolution that you have. Okay, 512 by 512 is a very good matrix to be using in imaging. Okay, so that you will see that number a lot. You can lower that matrix to acquire images in MR, for example, quicker, but you lose resolution. Okay, so 512 by 512 is a very good size matrix to be using for imaging. Field of view of 30, the field of view can be changed depending on your patient's body habitus. So in this instance, you have a field of view or FOV of 30 centimeters. Okay, first thing we're going to do here is convert the centimeters to what we want, which is millimeters, because remember, we're still using line pairs per millimeter as our unit. Okay, so 512 pixels over 30 centimeters is going to also equal 512 pixels over 300 millimeters. Now then we go to the second part of the equation where the reciprocal is the answer, so turn it upside down. 300 millimeters over 512 pixels is going to give you 0.59 millimeters per pixel. So remember what you have to do. You have to double that number, right, to get a line pair. So from the beginning of one line to the beginning of the second line, you have to double it. So doubling this 0.59 gives you 1.2 millimeters per line pair. Okay, and then one line pair per 1.2 millimeters is equal to 0.83 line pairs per millimeter. Okay, this CT scanner has a spatial resolution of 0.59 millimeters right here. So that's the smallest size of the object that you'd be able to see, or 0.83 line pairs per millimeter if we're using the units for resolution. Okay, now we're going to introduce a term called MTF, which is modular transfer function. This is just a fancy name for a way to chart different sizes, the ability to render objects of different sizes in an image. Okay, this is going to show, this chart right here is going to show you the higher the spatial frequency, the harder to image than those with low spatial frequencies. So higher spatial frequencies are harder to image than those with low spatial frequency. And if you remember, that red line that we had on that first chart had the low spatial frequencies over here. Okay, so we can see these large images very easily compared to the high spatial frequency, which are all these little smaller images. Those are harder to image. Okay, an ideal imaging system will produce an image that appears exactly as the object does, which does not happen, but that's our ideal that we're striving to. And if such a system existed, that MTF, that modular transfer function, would equal 1. Okay, so just the takeaway here is the measurement that we see, of course, is not going to equal 1 because that ideal system doesn't exist. So all of our systems have a measurement of MTF that tells you what the resolution is for that system. Okay, each system's different. Also, the line pairs become more blurred with increasing spatial frequency. And as you can see from this table or chart here, you see how the amplitude as it changes becomes closer together and shorter. Blurring starts to have an effect here, okay? So line pairs become more blurred with increasing spatial frequency, so at the higher end here. As the spatial frequency gets bigger, the line pairs become more blurred. Okay, MTF curves. So when the modulation of the bar pattern is plotted against the spatial frequency, you plot an MTF curve. So this is called a bar pattern, this up here. This is kind of like a test tool that you take pictures of. A physicist or qualified person plots points on these images that are taken with these test tools, and voila, an MTF curve is created. Okay, now what you guys want to take away from these slides are, remember, the ideal system has an MTF of 1. Okay, it doesn't exist. Everything is not exactly represented on an image, as we know. So each system, each imaging system will have its own MTF. Okay, most MTFs, as it states here, when an imaging system is evaluated with this message, the 10% line, that's here, right here, the 10% line, the 10% MTF, often is what is identified as that system's spatial resolution. So let's take this first slide right here. They've plotted these points and they've made a curve out of them, okay? And then they've made this dotted line on the 10% part of the MTF axis. And when they intersect that here, that gives them the line pairs per resolution, the line pairs per millimeter of this system. So this system with this MTF curve, the resolution equals approximately 8 line pairs per millimeter. Okay? So this is a normal radiography system. This over here shows you how mammography spatial resolution looks or is even better. Okay, so now they've plotted a regular radiography system with these test tools and a mammography system on one slide to compare. And this shows you at the 10% mark here, the radiography curve intersects at that 8 line pairs per millimeter, but the mammography line intersects at almost 15 lines per millimeter. So the resolution in mammography is much, much better. Okay? Also, I want you to take away as well, if you just pick any point here on this resolution axis, pick any point. Say we're going to pick 2, go right about here. If you intersect this, notice mammography is always better. It's always higher. Okay, so the MTF number is always closer to 1 than it is compared to radiography. Okay, so that's another. So mammography's MTF number is higher than radiography's number. Okay. Okay, this next slide shows Dr. Bushong. This is Dr. Bushong here in all these images. And by the way, that mustache is real. Okay, so this is just giving you a visual confirmation of the difference between mammography, which is here, letter B, mammography resolution in imaging, and radiography, screen film resolution. Big difference here. Okay, you can see the blurriness, very sharp compared. Look at this on the checked scarf here, very sharp, loses its sharpness. So much better spatial resolution in mammography compared to screen film. Okay. Okay, now we're going to compare mammography with DR. Now the MTF with mammography, as we know, is higher, closer to 1 than it was with traditional radiography. Okay, now what you're going to see here is in DR. Digital, there's this cutoff right here. So an MTF curve for DR has a cutoff. And this is because the MTF is determined by the pixel size. Okay, so remember, no DR imaging system can resolve an object that's smaller than its pixel size. So DR has a higher MTF even at these low spatial frequencies here. And that is due to an extended dynamic range, okay, and due to what is called higher detective quantum efficiency, or DQE. Okay, contrast resolution is the ability to distinguish many shades of gray from black to white. So this is the second major principle here, and we're going to get into dynamic range and DQE. All DR systems have better contrast resolution than screen film imaging. All DR does, okay? And that's why you have much more latitude on your images, and even when you use the wrong technique, you still have a decent image. Okay, and that's because you have better contrast resolution. So contrast resolution is our grayscale. And our grayscale is also defined as our dynamic range. And the dynamic range definition is the number of gray shades an imaging system can produce. Okay, the dynamic range for screen film imaging, remember our optical density was 0 to 3. Okay, which means that's 3 orders of magnitude. Its dynamic range went up to 1,000, okay? But viewers can only see 30 shades of that gray. And remember, with screen film imaging, you get what you get, okay? You have a single image, and that is it. If it's too dark, you got to redo it. If it's too light, you got to redo it. You get what you get, okay? But with digital imaging, the bit capacity of each pixel helps make up the range of the shades of gray that you're going to see. Okay, each modality has its own bit capacity. CT and MR, for example, are 12-bit dynamic range, okay, which is 2 to the 12th, and that's how many shades of gray you see. DR is 14-bit dynamic range, so 2 to the 14th power, and that's how many shades of gray we can see in DR. Not the visual eye, not the human eye, but with window width and leveling, we can discern all of those shades of gray. Mammography is 16-bit dynamic range, okay, and this is in table 17-2 in your book. Okay, this equates to 4 to 5 orders of magnitude, which is not important for you guys to remember. It's just something that's available to you. The dynamic range is greater than 65,000, okay? Okay, now, to get a little bit of what that means. The post-processing is the part of DR that allows, even with that high number of shades of gray, it allows you to be able to see all of those things. Okay, and that's why in DR, you can use an incorrect technique and still have a decent image that can be read. Okay, the principal advantage to DR is the pre and post processing. In screen film, like I said, you get what you get. Okay, A is an example of screen film. It's a decent technique for a mammography film, but it's limited because it's screen film. Okay, with DR, we can extract even more information. Okay, so this is our digital image that came out as soon as we pressed our exposure button. Okay, with post-processing digital, we see even more resolution because we can manipulate with the window width and the window level. This slide right here shows you if this is your original levels from white to black and all the shades of gray in between. With digital imaging, you can take just this little area and window width and level it again to see more shades of white and more shades of black. So this is increasing how many shades of gray that you can visualize exponentially. Okay, so with window width and window leveling, it is possible to view the entire dynamic range of grayscale. Okay, the next thing that we're going to talk about is signal to noise ratio, or SNR. The signal is the portion of the image-forming X-rays that represent anatomy. In other words, it is the difference between all of the X-rays transmitted to the IR minus those that are absorbed by photoelectric absorption. Okay? Noise limits contrast resolution. So having a noisy image will reduce your resolution. So we strive for a high SNR. Okay, you've got to choose appropriate techniques in Alera, though, because if you increase mass to increase your resolution to get a better picture, your signal to noise ratio is increased, which is what we want. It's high, but patient doses also increase. So there is a balance that you need to get to. So you can find the appropriate technique by your technique charts, okay, and utilizing Alera principles. Okay, next thing we're going to talk about is called a contrast detail curve. Okay, this is another method of evaluating spatial resolution and contrast resolution. Okay, the first curves that we talked about were just spatial resolution. This can be used for both. Okay, if you notice on this slide right here, this axis is contrast and this axis is detail or spatial resolution. Okay. The lower edge here of the detail axis is limited by MTF, okay, by your system's MTF number. When you get up to this higher spatial resolution part of your axis, noise is limiting this now, okay? So these two pictures here are tools, test tools, that physicists take pictures of on your system. And once the images are produced, for example, B here is an actual image of this tool, they perform QC tests on the image to get the information that they need from these images. Okay, and that is how they can evaluate the system's resolution, either spatial or contrast in both. Okay. So these contrast detail curves look like this. So for instance, this curve right here on the top is two different systems, one with a better resolution, this 150 millimeter pixel one, versus the 80 millimeter. This curve right here shows what can happen at the same system when you use high mass versus low mass. And this curve here, this slide here, just shows different imaging systems and how their curves differ, okay? Remember, spatial resolution is limited by the system's MTF number. Contrast resolution is limited by noise or SNR, okay? Dose creep. We've got two more slides. Hang with me. Dose creep. This is an important concept for you guys to realize happens out there and try to prevent it, okay? With digital radiography, we should be lowering patient dose, remember, by a factor of 20 actually, but we should be lowering patient dose by 20 to 50%. But frequently the opposite occurs, and this is due to dose creep. It is caused by technologists' poor practice, okay? They're not utilizing appropriate exposure techniques. They are not thinking Alera through. Okay, they are not paying attention to the techniques that are actually on the control panel, and that is because they're used to these nice images coming out, and they know that the images can be manipulated and acceptable for diagnostic purposes. However, that does nothing for your patient, okay? What is happening is patients are being overexposed dose-wise, okay? Even though we don't need to take a repeat due to overexposure or underexposure when we're using digital, because the contrast is pretty much constant and you get a decent image either way. This shows what happens on traditional conventional radiography with improper technique. This shows what happens in digital radiography with improper technique. Hardly a difference that you could tell without magging it up and looking like we did in lab. So it is up to you guys out there, and we are training you to be diligent, okay? Even though your contrast, your resolution is constant, you still need to use the appropriate dose and do right by your patient and prevent dose creep, okay? Okay, last thing we're going to talk about is called DQE, which is detective quantum efficiency. And this is a measure of X-ray absorption efficiency. It is very dependent on X-ray energy levels. And what this is each screen inside your IR has a measurement to it based on what material is absorbing the energy of the X-ray. And for example, cesium iodide, which is one of the most popular materials in DR, it has a very high DQE. So it's very, very efficient at utilizing X-ray energy to make to make an image. Okay, so it's very, very efficient, in other words. So you need fewer X-rays are needed to produce the image, thereby lowering the dose. So actually, we should be going in a downward trend where there's a lot less patient dose out there. So you guys can be on the forefront of trying to incorporate this and get people to change their habits, okay? So patient dose in DR should be low due to the high DQE of the IRs that we're using out there. And this supports using higher KVP and lower mass in digital radiography on all of your images, okay? All right, that's all I have. That's chapter 17. You guys study hard. We've got our exam number 2 in 1 week from today. Okay, so next Friday, it will be covering chapters 13, 15, 16, and 17 of Dr. Bushong. Okay, so chapter 13 is the screen film radiographic technique. 15 is computed radiography, or CR. 16 is digital radiography, or DR. And this is 17, digital radiographic technique. Okay, so read through those chapters. You've already done your homework. Look through the PowerPoints that are out there. Go over your notes. And hopefully everyone will do well. And I will see you next week. Have a great holiday.